we're going to talk about non-homogeneous linear systems. So systems that take this form. Now, when I solve it, I would really like to know the solution. In particular, I'm looking for the general solution, every answer to this problem. So this is going to be straightforward to obtain. So let's say that XH is the solution to x prime equals AX, the homogeneous problem. So that means anytime I plug in this thing XH, it will satisfy this differential equation. So let's say that XP is a particular solution when the homogeneous equation is when the homogeneous solution is the trivial solution. So that means that XP prime is equal to AXP prime plus F. And just for fun, let's say that X is the general solution, so every answer. And that means that X prime equals AX plus this thing F. So let's talk about the following. We know that F has to be XP prime minus AXP, but it also has to be the general solution, X prime minus AX. So that means we can take these two things together and say that X prime minus XP prime, those two things have to be AX minus AXP. If I put this together, I can combine this by linearity, and that's the key here. Linearity tells me that the following will be true. That I'll get A into X minus XP. And that means then that this function has to be the homogeneous solution, because this combination satisfies the homogeneous differential equation. And that tells me right away that X minus XP has to be XH, or the general solution is always a sum of the homogeneous plus the particular. And that is exactly like it was for scalar equations. And it's no surprise. This will be true for all linear problems. So we find XH as before, and that could be typically an eigenvalue problem, and for a constant coefficient problem. And so now the question is, how do we find this particular solution? There turn out to be a lot of different ways we can try to attack this problem. And we'll start with the most straightforward one to think about, undetermined coefficients. And that means that the form of this particular solution is going to be proportional to the driving force. And this is exactly as it was prior, right? We are going to assume that the nature of the driving force F will induce a response from the system that will be of the same form. So for example, if our driving force is a constant, then we should try a solution, a particular solution that is a constant vector. If my driving force turns out to be some linear function, then we'll try the most general linear function we possibly can. Now, what's important here is that these constants are constant vectors, not scalars. For example, if we have a driving force that is exponential, where we have some, I should be careful here, that t is not the vector, it's a constant. If we have some constant vector e to the alpha t, we should try one of two things. We could try something that is e to the alpha t if it's not in this homogeneous fundamental set, or we could try xp is a t plus b e to the alpha t if we are in the fundamental set. And as we did earlier on in the course, there are many options by which we can go ahead and do this. So the most straightforward thing to do is just show you. Let's go ahead and start tackling some of these problems. Now, we are going to consider the same differential equation for all of these particular questions. We'll have the following 2x2 system. We can illustrate all the ideas very nicely with our 2x2 system. The details just get worse and messier. So here's an example of a non-homogeneous system. We know that the general solution has to be the homogeneous problem plus the particular problem. And as always, what we are going to do is go ahead and find the homogeneous system, the homogeneous solution first. We need to find the fundamental set. And that means we have to solve x prime equals ax. We will always try that this homogeneous solution should be e to the lambda t for a constant coefficient problem. Without going through the details here, it will turn out that lambda is -1 and -3, and that the homogeneous solution will be a linear combination of the following: 1, 1, e to the minus t, c2, 1, -1, e to the minus 3t. So you can pause the video, try that out for yourself. This is just review. Now, if we take this function f, if we take this right-hand side to be, for example, the vector 1, 2, so it's a constant vector, we are going to try a particular solution that is also a constant vector. In a 2x2 case, that means we've got two unknown components that we have to figure out. So our task here is to figure out what these two undetermined coefficients are. And to do that, what we have to do is sub this into our differential equation. So if xp is just a constant, we need its derivative. So its derivative will simply be the 0 vector. Now, when we plug this into our system, x prime equals ax plus f, here's what we're going to get. We'll get 0, 0 on that left-hand side, sorry. And our matrix is -2, 1, 1, -2. And now we're going to be multiplying by this unknown particular solution that we're trying to guess the form of. And here is our left-hand side, our driving force 1, 2. So this is going to end up giving us the following vector system. We'll have 0 on the top entry, -2a1 plus a2 plus 1, and a1 minus 2a2 plus 2. So we get a system for a1 and a2. And that system looks like this. -2a1 plus a2 is -1. a1 minus 2a2 is -2. So all we need to do is reorganize this. So we can put this into matrix form to try to deal with things a little bit more straightforwardly. We can do some row reductions. And we'll just walk through. Remember, we're trying to do Gaussian elimination, so we have a pivot in this top position. We're trying to create a 0 below it. So we'll take 2 bunches of that top row, add it to here. 2 bunches of -2 added to there will give me a -3. 2 bunches here is going to give me a -5. So if I keep row reducing this, I'll get 0, 1, and 5/3. And now, once we get to this value, we're going to multiply this by 2. We'll have 10/3 minus 6/3 will give us 4/3. And at the end of the day, we have found what we're looking for. A is 4/3, A2 is 5/3, and that means that the particular solution has this form: 4/3 and 5/3. And in essence, this is how the method works. We guess a form of the solution. We figure out the homogeneous first, and then we guess a form for the particular solution. and we sub it in and try to determine what those coefficients are going to be. In principle, that's as easy as the method gets. Now, as before, once we have non-homogeneous problems, we can see here that these terms are the transient terms. They will both die out as time goes to infinity, and what we'll be left with here is this steady state. Now, in principle, the method works exactly the same regardless of the driving force we've got. If we take, for example, the driving force on this right-hand side to be a linear function, so 0 and 6t, that means we need to try a particular solution that is proportional to that driving force. The driving force is linear, so let's take the most general linear driving force that we can. So we'll take an AT plus a B. In the 2x2 case, remember that this is going to work out to 4 unknowns that we need to figure out. Differentiating them is going to be required, so when we take xp prime, this time we aren't going to get a strict 0. The t term is going to give us a contribution, and we have to sub this into the dE. And when we sub this into the dE, we have to make sure we account for everything properly. So the x prime term is going to give us an a1, a2. We'll have our matrix 2, 1, 1, negative 2. And now we have a bit of a mess here, right? So we can write this as a1, a2 times t, and b1 and b2. And to this, we are adding our right-hand side. So we'll have a 0, 6, and a t. So we want to use definition of matrix vector product. And so we'll get a negative 2a1 plus a2, all of these terms times a t. And I'll be careful about how I write this. We'll have a negative 2a1 plus a2. And, sorry, just 1 second here. And in that bottom entry, we'll have again a1 minus 2a2. All of these terms are going to be weighted by this scalar factor of t. And at the same time, this matrix can multiply over there. We'll get negative 2b1 plus b2, b1 minus 2b2. And don't need this bracket. And we'll have the 0, 6, and t. So how do we make sense of this? What we need to do is we need to equate powers of the variables that we see here. So we are going to equate powers of t on both sides of this equation, of this system. So t to the 0, we have 0 and 0. We have no, actually, this is not correct. We do have powers of t to the 0. We have constants. So we have a1, a2. I guess I'll color code this. There's a t to the 0. Here's the constant on the left. And so it must match the constant on the right. So this will give me negative 2b1 plus b2, b1, 2b2. And then powers of t on the left, we have none of them. So I'll put a box here, I guess. We'll have a 0 box there. And then these powers of t exist on the other side. And so if we go through this, it's just a matter of bookkeeping, right? We have to keep everything straight here. So we'll have the 0, 0 vector on this side in terms of the t. And on the other side, we'll have negative 2a1 plus a2 plus 0, a1 minus 2a2 plus 6. All of that multiplies by t. So we end up getting two systems. Now, you could think of it as two systems or one giant system, but there are 4 unknowns that we need to solve for. And so we'll have negative 2a1, a2 equals 0, a1 minus 2a2 equals -6. That comes from the purple system, if you want to think of it that way. And then the other system we need to deal with is -2b1 plus b2 is a1. b1 minus 2b2 is a2. Now you can see that the A system does not require b's. It's not coupled to the b's. So you can find the A system, and then once you have the values of A, you can plug them into the right-hand sides there. Your other option is you can write this whole thing as a 4x4 system and solve at once. The choice is up to you. However you'd like to do it is fine, but you will find, in this particular case, you will find that A1 is equal to 2, A2 is equal to 4. You can simply solve system 1 to get those values, and then once you've got system 1, you can go ahead and solve system 2. You can basically solve this problem, and what you'll find is that B1 should be 8/3 and B2 should be -10/3. So the undetermined coefficient method is nothing but bookkeeping. Way back when we decided up here to determine the form of our solution, we have now found it. So the particular solution is this AT plus B. So we've just found that we'll get 2, 4 into T, 8/3, -10/3 as that constant term. So there's nothing glamorous about it. It's just an efficient method. You can go ahead and you plug everything in to solve it. Now, as we've encountered before, the only hang-up that could happen is when your driving force is part of your fundamental set. So note, this is part, I should say like this, F is part of the homogeneous solution. So if you try a particular solution that is some multiple of e to the minus t, it won't work. You'll end up with contradictions. So what you have to do instead is, as before, try a particular solution that bumps up the power of t. You have to try a e to the minus t, where a is a constant vector, and then b, another constant vector, t e to the minus t. So this adds an additional layer of complication. This term is needed because you need to account for the right-hand side in some way by using terms that are not in the fundamental set. You'd have to differentiate this term, so you'll get negative a e to the negative t. You're going to get 1 times e to the minus t plus, or I should say minus t e to the minus t. So it ends up being kind of messy. You can treat this in lots of different ways, but it's in terms of solving a system. Remember that what we are looking for are two unknowns from the vector A, and then these two unknowns from the vector B. Nothing glamorous about it. I would recommend that you put these two together. You'll get negative A1 plus B1, negative A2 plus B2, e to the minus t, subtract t, B1, B2, e to the minus t. That goes on your left-hand side. On the right-hand side, you're going to have to sub in and multiply all of this. So you'll have a times xp, which is going to give you -2, 1, 1, -2. And then you're going to get this combination of terms. So you'll get a1, a2, e to the minus t, b1, b2, t, e to the minus t. So there's not much more to it other than to just plug everything in and multiply it together. As before, you're going to get a giant system. So you're going to have to plug it all in and combine terms. So you're going to have to match the powers of e to the minus t and t e to the minus t on the left-hand side and the right-hand side. You're going to have to match them. This is going to lead you to a system for A1, A2, B1, B2. You can either do it as two systems or one giant 4x4 system. Either way, it won't work. And I shouldn't say it won't work. It will certainly work. But in this case, it's probably easiest to go through and solve it as a 4x4 system. And what you're going to get to is you're going to get to a solution here. You can find that xp is going to give you the following. You'll have that A1 3 plus A2. A2 will be free. That'll be e to the minus t. And B will be 3 t e to the minus t. Once you go through, you can select A2 is 0, and you can find that the most straightforward form of the particular solution will look something like this. So, undetermined coefficients, nothing glamorous, but it gets the job done. In the majority of your cases, it's kind of the workhorse method. There are other more sophisticated methods, but they end up being more cumbersome to use as you work through things.